Alright, welcome back to our video series where we're performing a heat transfer analysis in heat sinks. In our last video, what I did was I described a computer setup I had to build about a year ago, which had a pretty beefy heat sink in it. What I have here is the heat sink I actually put into the computer. As I explained, it's a Lagrange Macho RT. This is a work of art, a work of engineering, and what we intend to do in this video series is take a look at how we can derive a temperature distribution which describes the heat flow through this guy and helps to explain how we keep our computer equipment and electronic equipment nice, cool, and effective, okay? So in that video, what we did is I provided a brief overview of different heat transfer mechanisms. For example, we talked about conduction and convection. Okay? And then what I did is I derived a non-dimensional parameter known as the BO number, which we're going to make use of extensively in this video and subsequent videos within the analysis, which is going to drastically simplify the problem we have to solve and give us great analytical power. Now, what we're going to do in this particular video is we're going to continue that discussion and take what we invested our time in, our hard time deriving that quantity, and try to use it in deriving a temperature distribution. In this particular video, we're going to focus on taking a look at the equation of motion that's going to be used for solving this problem, and then we're going to derive the different boundary conditions and use them to make it a simpler problem, to make our lives easier, okay? So let's jump straight into the problem. Now, as you can see from this picture right here, this particular heat sink is pretty convoluted, pretty complex. We got a lot of fins going on here, a lot of geometry. The engineering that is packed into this is super hardcore, okay? So in order to do this analysis, to derive an analytical solution without using any kind of finite element analyses, what we're going to do is we're going to simplify the problem by using several assumptions. So as we talked about, the pipes that run through this heat sink, you can see popping out here, these little spikes, they're made of a material that's very conductive, which means that the heat tends to spread out through this apparatus, if you will. What we're going to do is we're going to assume that the temperature is constant, in essence, okay? And we're going to do that by taking a look at a very similar type of heat sink, which is much more simpler, much more straightforward. This was used, it's sort of like an archaic design. It's used maybe 10 years ago. Sometimes it's used still on motherboards. Sometimes it is used on lower-end processors that don't have to dissipate as much heat. So what that actually looks like is it's like a base plate on top of your CPU, and then you have fins that come up. Just like the Lagrange Macho RT, this type of design of heat sink, it tries to maximize the contact area of the air that's flowing over it so you can get more convective heat transfer and dissipate that heat more quickly and more effectively. Okay, so that's the analysis we're going to do. And to simplify that, we're going to take a look at one simple fin. Okay, and that is depicted here as follows. So we're going to have a ton of those fins along the base plate. They're going to come up, and then the fan is going to blow air over that. We're going to get convective heat transfer as I described, and it's going to get dissipated out of the apparatus. So if we take a look at one fin, and we assume that the temperature in steady state, that's the key word, steady state, is constant throughout the base plate, then we know that each fin is going to exhibit the same kind of temperature distribution above it, okay? So we're going to focus our attention on one single fin of that heat sink apparatus. Okay, so what I described here is one single fin. I'm going to assume it has a thickness of 2W. W is sort of, that's sort of hyphenated for width. And then it's going to have some kind of length at which it comes up above that base plate, which we're going to signify as L. Okay? So what you notice here is that what I selected for our axes is I'm assuming that our axis is going to be in the middle of the fin. Now, as we go through the boundary conditions, that's going to elucidate why I made that choice and why it simplifies our analysis. But for now, I'm going to ask you to just go with it. You can put the axis wherever you want. This is going to be the most effective choice for the analysis we're going to run through today. Okay? So we're going to put an XY axis as such. I just chose to make the x-axis go up and the y-axis go straight across the length of the fin. And there are two conditions that we know to be true, right? What we know is that if we have a constant temperature base plate, that's an assumption. That's what we've fed into the design, right? That's selected by design. So we know that at y equals 0, all along this base plate here, in the x direction, it's going to be set to some base temperature that I specify as T0 here. Okay? The other thing we know is that there's going to be a set temperature for the ambient temperature, the temperature of the room all around us. Okay? So we know that when the fan blows the air past this fin, that's going to be the temperature that interacts with the fin along the surface. So what we assert is that far away from the fin, in every x direction, when y equals infinity, we have this guy here. We're gonna assert that the ambient air temperature condition is as follows, that it's T infinity. Okay? That's gonna be room temperature, whatever it's gonna be. Obviously, the lower that temperature, the better and more effective your convective heat transfer, right? Why? Because heat transfer is driven by temperature gradients. So if you're a higher temperature gradient, the more effective your system is going to be, okay? All right, so this is the general geometry we're going to work with. And what you do in any kind of physics problem is, the first thing you want to do is you want to come up with your equation of motion that describes the physical process that's taking place. In this case, we're going to analyze everything within this fin right here. And the physical process that we're analyzing is conduction. And when we use our boundary conditions, that's going to be connected to convection, right? We're going to find that we don't want any discontinuities, so we're going to have to make the heat transfer from conduction equal to the heat transfer from convection along these boundaries where that is actually occurring. Okay? But in terms of the equation of motion we put together, right, that's the starting point. That is like the blueprint, the treasure map, if you will, that allows us to go out and find the actual value, what we're trying to find, the temperature distribution, the end result, okay? So the equation of motion is going to dictate how the heat is going to dissipate throughout this object and eventually get pushed off into the air and dissipated out of our heatsink, out of our device, and allow us to attain the main goal we're trying to achieve, okay? So that blueprint, which has all the directions we need for deriving that temperature distribution, is as such. Okay, I'm not going to derive it here, but a common result, and I can derive that in a separate video if you guys are interested. And I'm just going to put it up here and give you the full form and then simplify it, okay? So the equation of motion is known as the heat equation. And this describes the way in which heat, temperature, and energy flow throughout and are dissipated within a heat sink, okay? So this is the beginning stage for any problem. And what we want to do now is go over what this heat equation is to give you some kind of footing, some kind of intuition when we're running through this, okay? So it is as follows. What we have is the partial derivative of the temperature distribution, and we're going to assume it's in terms of x and y. We're going to assume these fins are very long in the z direction, which means that we can neglect that direction, okay? So we have a non-steady state term, which we have to account for how the temperature is going to change with time. Basically, in physics, we have a lot of systems where initially we go from one state to another state. We have a transition phase, and then we have a steady state phase where, you know, there may be changes, but it's a consistent change. It's a steady change, as the name applies, okay? So eventually that transition phase is going to be knocked out, and then we're going to have a steady flow of heat, a steady flow of conduction and convection, and any point within this, that temperature will not change with time, okay? So initially, in that transition phase, we need to account for a non-steady state term, which is this dt, okay? Next, what we have on the left side of this equation of motion is a convective term, okay? So remember what you learned in the last video. What is convection? Convection is a way of transferring energy and heat through the motion of particles, the motion of some kind of fluid. In this case, with the Lagrange-Macho RT, we have this fan blowing air over it, and that's pulling out that heat from the actual metal, from the different surfaces that are exposed to the air. So this term here is going to account for that convective nature, okay? And as you can see here, if you have flow of mass, you need some kind of volume flow rate, some kind of velocity, so on and so forth. And that's what we end up with here. So, we got a velocity times each gradient in each direction, okay? So if it's pulling it in the x direction, we have this temperature gradient in the x direction, in y, and in z. This is a Cartesian format of the heat equation. There are other forms, right? You can have a spherical definition of this. You can have it in cylindrical coordinates, and it's going to be a little different. But for our problem, since we're dealing with rectangles, and you look at this heat sink here. The fins are rectangular. They're Cartesian by design and by nature. Okay, so for that reason, it's most easy to approach it by using a Cartesian system. Okay, so that's why we're using x, y, and z in this equation here. Okay, so we have non-steady state terms, convective terms, mass flow carrying the energy out. And what I want to make note of before we move on is that they have the same units, right? Everything on the left and the right have to have the same units. So this guy here has units of some kind of temperature. We're going to go with Kelvin per second. So here you can see the same thing because this is sort of Kelvin per meter times meter per second. That gives you Kelvin per second. So we're good. The convective term matches up with the non-steady state term, okay? So that's the left side. This all has to be equal to what is on the right. The first term we have is a term for conduction over the boundaries. So this is sort of like if you take a slice of this fin right here, you're going to have heat transfer from this portion into that portion. So it flowing through that metal, through this constrained volume, or area in this case of the board, that is governed by this term here. Conduction over that boundary in that direction, remember? So we're going to have three separate directions which conduction can occur. X, Y, and Z. And in the front here is just to make units consistent. This is the conductivity of the material that is present. So if you look up, parameters for different materials in an index, in a book, or even online nowadays, you're going to find parameters known as conductivity. That's sort of like the conductivity we explained previously, but just a little different. Little different terms at play here. The final term here, which I have not written down here, and I will do that right now, real time with you guys, is known as a source term. I'm going to write that down here, source term. And it may be labeled different things in different textbooks. What I've used here is a HV, which is a source term over the volume, over rho, the density, and the specific heat, CP. Okay? What this accounts for is if energy is generated within the material. How can that happen? That can happen with electricity in wires, for example. If when you hold a wire and the electricity flows through it, that electricity generates heat. Okay? That would be this guy. It's being produced within the material, so you need to account for that. In essence, what this is just an energy balance. Energy flow on the left equals energy flow on the right. Okay? So that's the source term. I want to back up a bit and go back over the convection term. So I gave an example of a source term, how heat can be generated inside this device. I want to give an example of convective terms. Right? I gave an example here. You could have air flowing over it. Another example is the material within the system actually flowing. So for an example, the best example I had and problems I solved in grad school was wax from a candle. So if you have wax from a candle, the material can melt and it can flow. That flow, mass flow, can carry that energy out of the system or around the system. That is described again by this convection term. So here is a nice balance that's derived by considering the flow in, heat flow in, and the heat flow out. These guys have to be equivalent. This is the blueprint. This describes how heat flows throughout our device. And by using this blueprint, using this treasure map, it can direct us where to go. It can direct our analysis down the specific path we need to travel to yield that final result we want, to yield that temperature distribution, which is going to help us understand what's going on in this device. And if you're an engineer, help you design the different geometry, give you that information you need to get that end goal, that end product you're looking for. Okay? So this is our equation of motion. This is the baby that has all the answers, all the information. We use this to derive the solution. We got to solve it. The problem is, and I know what you're thinking, holy crap, right? We've got a temperature distribution which is dependent on x, y, z, also time. It's nonlinear. We got second derivatives here. Crap, this is hard to solve. So when you run into a problem like this, the first thing you want to do is you want to take a step back. You're going to take a look at the situation at hand, what you're describing, and see if you have any kind of conditions, terms, so on and so forth, that can help you simplify it, simplify your life, such that you can reduce it down to a state that is solvable, that doesn't make your head freak out when you actually look at this. So let's do that right now before we jump into the boundary conditions, okay? So if we do that, we can take a look at two simple conditions that will greatly and significantly simplify this huge, long, partial differential equation, which is very complex. What are those conditions? The first thing I want to make note of, and I sort of talked about this previously, is that initially, any kind of physical system is transitioning from a dead state where nothing is happening to where stuff is moving, right? You have to transition from rest to your steady state condition, okay? That transition changes temperature throughout a device, throughout this fin with time. However, at some point, that term is going to fall out. You know, you would have an e to the minus whatever, so it doesn't have any kind of contribution as time progresses, like e to the minus t. So when t gets very large, it's essentially 0 for that term, and it doesn't contribute to the final result. You're going to have a steady state solution, which gets picked up, and then any point in this guy is going to be the same temperature, even though energy is still moving through it, okay? I hope that doesn't confuse you. It's steady state in the sense that the temperature distribution does not change, but energy is still flowing through it, okay? A little contradictive. This pops up quite frequently when you're solving simple, ordinary differential equations, where the solution is going to have a transient portion and a steady state solution. This happens a lot in my UDEMY course, which you can check out if you want on classical physics. I run through a lot of examples where we're solving those differential equations, and again, you end up with that steady state solution and that transient solution, and usually the transient solution is like e to the minus something t. So as time progresses, it doesn't have a huge contribution to the solution, okay? So if we make note that we're only going to analyze this at steady state, and that makes sense for our situation because you start up your computer, it starts transitioning, right? That CPU does some computation, right? You get this guy generated. This is a source term inside your CPU that generates that heat. It starts warming up the base plate of your heat sink, or maybe the tubes that are running through with all these fins. And then eventually, you're going to start getting this constant temperature. It's going to be very hot until you change your condition, right? Until you put on maybe a video game, you do some video processing, so on and so forth, which is computationally intensive, needs more electricity, generates more heat, and then you have a transition to a different state. We're going to take a look at a steady state. We're going to assume that, let's say we put up an application that consumes the same amount of energy at a constant rate, and that sets the base temperature of the base plate of your heat sink, that one temperature, and nothing changes. So in that kind of scenario, in steady state, the temperature distribution is not dependent upon time, and that allows us to say that the partial derivative of the temperature distribution with respect to time is 0, and this guy right here is going to pop off, okay? So this guy is going to be, whoop, that drops right out, okay? The next thing we're going to do is we're going to take a look at the convective term, okay? So obviously, we have convection in this guy. We're blowing stuff over the fins, but we're restricting our analysis to the fin in and of itself, right? Just the fin, just that volume. So the air is outside of this guy, right? We're not interested in the heat conduction, the heat convection, the heat transfer outside of our device. We're not interested in that. So the question I have for you is, if we only take a look at the analysis inside this box, inside the fin. Is there any mass flow over that? Is there any mass flow? This is a solid metal. It's a solid material. So unless it gets super, super hot, that it melts, which is not going to happen because then you have other problems. Your computer is toast. This guy is solid. It's not going to melt. There is no mass flow within the metal, within the fin. Okay? This guy, the velocity of the material, Vx, Vy, Vz, is 0. Okay? So what that does, that drastically simplifies our equations because we can say that's 0, that's 0, that's 0. We get a 0 over here. Now the final thing, which should be obvious, which I had not noted under here, which should be number 3, is that the source term, HV over rho Cp, that's also going to cancel. Can you figure out why? Why would that cancel? Well, if you have a heat sink, as such, you're not running any kind of electricity through this. Nothing is melting. Nothing is burning. You have no chemical reaction inside this guy. You're not generating heat in it. And that's by design, right? The metal is intended to allow the heat to flow through it, transition or interface with the air that's flowing over it, and get dissipated, right? That's the whole intention of a heat sink. That's what the name implies. So what's going to happen is there's no electricity, there's no chemical reaction. The source term is going to be 0. There's no energy generated within our system. It's only flowing in and flowing out across the boundaries. And that's what we're going to tackle next on the boundary conditions. But before we do that, what I want to make note of is if HV, the source term, if no energy is generated in, that's 0, that pops out, and we're left with the following. The final simplification we're going to use is we're going to assume the fin is very long in the z direction, infinitely long. So in that case, we're not going to have any heat transfer in there, okay? Just because the heat is going to spread out very quickly in this material. It's highly conductive. And as a result of that, you're going to have no temperature distribution. You're going to have no heat transfer. If you do in real life, it's going to be so minimal that the quantity of it, it's going to be so small when compared to these two guys, right? It's only going to flow in the x direction to go out here into the ambient air, or the y direction to dissipate out off of that tip, okay? So as a result of that, this guy also cancels, and what we're left with is just two terms. Much simpler, okay? We end up with the following. We can get rid of this guy right here, and we just get a second derivative of temperature in terms of x and y. They're added together, and they equal 0. So, moral of the story. This heat equation, the partial differential equation, super complex, super convoluted, but if you're cognizant of the different conditions that exist in your system, that can drastically help you simplify this by kicking certain terms out of that equation and simplifying it from that big long guy down to something that's very nice, very elegant, and only has two geometrical quantities that the temperature is dependent upon, okay? So, this is much simpler than this guy, but at the same time, we have an x and a y, two dependent variables, or rather independent variables, sorry about that. T is the dependent variable. So it's not as simple as you may think. It's sort of coupled, if you will, the y and x terms. So what we're going to do after we run through the boundary conditions is we're going to work on trying to simplify this further so it's in a state that we can quickly solve using like ordinary differential equations, get an answer, get results, and figure out what that temperature distribution is going to look like. Let's take a look at the boundary conditions next. All right, so we just derived the equation of motion, which is sort of like the treasure map that is going to provide all the information to guide us to the final solution, that final temperature distribution. Now what we need to do is we need to take the information inside of it and use the physics to end to our final goal. And that is going to be done by deriving our boundary conditions along every surface of the geometry we're taking a look at. In essence, what we're trying to assert is that we don't want any discontinuities in our temperature distribution. So when we have conductive heat transfer from maybe the center line here that goes all the way to this surface here, where air picks up that energy and flows away, we need to make sure that the heat transfer is consistent between these boundaries such that we don't get any discontinuities, right? Nature likes to behave in a nice, orderly fashion. It doesn't want to do things where it jumps erratically and changes in a minute, basically instantly, right? Nature does not behave like that. Nature behaves in a smooth fashion. It doesn't have any discontinuities. So in order to get a valid solution, in order to conform to what nature is dictating, we must assert that there are no discontinuities. That's where the boundary condition comes in, and that's where the physics come into play when we're using our map, right? The boundary conditions are sort of like your compass, your walking boots, so on and so forth. When you combine all the packages together, all that information helps you get to the end goal, all right? So let's derive the boundary conditions, all right? In order to do that, as I said, we're going to guarantee that there's no discontinuities along this edge, this edge, this edge, and that edge. So what that means is there are 4 areas, 4 edges. We're going to have 4 boundary conditions. The first one is quite straightforward, and it is dictated by the design of the problem, right? The problem we're looking at is either in our heat sink here, this guy, either having a constant temperature along these tubes, or in the simplified version, that base plate having a static base temperature. We asserted that at y equals 0 along the x-axis, we're going to have a steady temperature. It's going to be constant, all right? So the first condition we have, we already really know. That asserts that basically Tx0, y equals 0, is equal to T0 along this boundary. Bam! We're already done one. That was super easy, right? It gets a little bit more complicated. Next, what I'm going to say is I'm going to tackle probably the hardest one to conceptualize, and I'm going to walk through it with you. And then we're going to take a look at conduction versus convection, which is going to harken back to some of the concepts we discussed in the first video of this video series. But before we jump into that, let's tackle the hard one first. And this has to do with symmetry and sort of elucidates the reason why I picked our axis to be right in the center here. Now, if we assume that the heat transfer constant, H, for convection, right, HA times the surface temperature minus the ambient temperature, that's the convection heat transfer equation, if that is constant, and our base temperature down here is a constant T0, and it remains the same along the x-axis, then it is appropriate to assume that the maximum temperature occurs at the center of the fin. This creates a symmetry to the problem. What am I talking about here? That's a big assertion. It's very important to understand that. So let's walk through it. So, if we have temperature and energy constant here, what we know is that as it flows into this fin, there are mainly 2 routes in which heat can flow out of it, right? So it's going to flow in here, and then, the temperature gradient drives the heat transfer. We're going to have a temperature gradient from heat here, the very low temperature in the ambient air that's flowing across it. That's going to pull the energy and the temperature down as you move in the x direction, right? Energy wants to flow in and then out, or in and then out, okay? So that means that if temperature change, temperature gradients drive that heat transfer, the temperature has to drop as you move towards this surface, right? That is the physics. That is what's dictated our heat transfer equations, okay? So if it has to drop in order to drive that heat transfer, this has to be the maximum amount because it's not going to flow into the center. It's flowing in and then out. So when I was taking heat transfer actually I had an undergrad course in it, in a mechanical engineering curriculum, what we had to do is we had to actually draw temperature distributions without actually doing any kind of math, any kind of physics. And I got pretty good at it. And that helped us derive boundary conditions like this. It gave me good intuition in terms of this, but you may be a bit confused. So I'm going to draw that up, try and explain and elaborate a bit more than what I just described. So, the maximum temperature, what we see here, I'm going to go down here. Conduction is negative Ka times the derivative dt dx, right? So if we have a derivative, that's going to signify heat transfer. So initially, right, it wants to go down here, so we need some curvature, right? And then we're going to have a different curvature for the convection, which is going to be dictated by the convective heat transfer. And that creates a temperature distribution as follows, where this is x equals 0, right in the center. It has to drop off to drive heat through these surfaces here. And you get something that's sort of like an error function here. So we have drop off, and then it goes to the ambient temperature far away from the fin as x goes to infinity. Okay? So what we see here, the maximum temperature is at the center of the fin, and that's because nothing crosses the center, right? If we look at the conduction portion of this guy here, if the derivative is 0, you have no heat transfer. The derivative is here, so it's not crossing the boundary, right? And eventually, as time progresses, if you turn off your application, turn off your computer, this heat is going to spread. The energy is going to spread out, right? And that's going to drive this maximum temperature down as it flows out the sides. So it's flowing from the max out to the sides. That's dictated by the physics. That's dictated by the nature. So eventually, we're going to get some distribution that looks like this, where the heat dissipated into the environment, raised the temperature of your surrounding air, and we get some straight temperature distribution all across your guy here. It's going to be T infinity, the original ambient temperature, plus some delta T, okay? So, the important thing to note, based upon this graph here and what I said here, that no heat flows through it, and that conduction has this derivative here, is that dt dx has to be 0. We can see it through the slope here. If we use, Calc 101, right? This says dt dx equals 0 when x equals 0, right? So right in the middle, x equals 0, all along this fin, no heat can cross it, and we have this nice symmetry here. That dictates the following boundary condition, which is known as the symmetry or heat fin equation approximation. So it's dt dx at x equals 0 along y equals 0. Okay? So now we've got two boundary conditions that we're going to use. And this sort of elucidates why I chose the center. I chose the center because if this is symmetrical, we know that this side, this temperature distribution, has to be the same as that side. It's just in the reverse direction. So what we can do now is we say, okay, well, all I have to pay attention to is this little chunk here, because heat transfer here is going to be the same as that. That's why I chose the center of this fin. It was guided by my intuition, guided by this fact, and guided by the reality that no heat transfer is going to cross that border. Right? It has to be the max, as dictated by Fourier's law. Okay? So, we're just going to look at this portion here, and that means that if we have a boundary condition here, we need to account for the heat transfer across this surface and this surface. Okay? The way in which we do that is by taking a look at how the heat transfer is occurring right here. So I have this green circle here. We're going to blow that up down here. And what you find is that the heat that's flowing, right, this is the max temperature, so the heat has to flow out to low temperature, right? The temperature differential drives the heat transfer. We find that conductive heat transfer is going to flow towards the surface. The air is going to pick up that energy, flow away, dissipate it. So we're going to have conductive heat transfer up and convective heat transfer out. Okay? So this, we can do an energy balance. Energy cannot be created nor destroyed. So what that means is that what flows into this boundary has to flow out. Otherwise, we violate physics. Otherwise, we violate the natural laws. Okay? So what we could say is, okay, at this boundary, in order to get my boundary condition, which is going to help us solve our equation of motion, we see that the conductive heat transfer has to equal the convective heat transfer. Or in other words, Q in equals Q out. Heat transfer in equals heat transfer out, okay? So we know from the last video, we derived Fourier's law for conduction and Newton's law of cooling for convection. We can just plug those babies in and see what we end up with. So we know that from Fourier's law, conduction is negative K conductivity times the area it's flowing through, which would be the top area of this guy, times the temperature differential, which is driving that heat transfer at the boundary. So in this case, this temperature differential has to be the temperature differential across the boundary. So in this guy, we're going to have to go in the x direction. This guy, we have to go in the y direction. So for now, I put dt dx just to have some kind of derivative in there at the boundary. And we know that this has to be equal to the heat transfer coefficient h times the area it's flowing through, either that guy or that guy, times the surface temperature, which would be right here, right there, minus the ambient temperature. Okay? So if we take this, we know that the area is the same. We can cancel that guy out. Divide the negative k over here. The boundary condition we get, the derivative, is going to be equal to negative h over k times the quantity Ts minus T infinity. Okay? So we're trying to eliminate this discontinuity at the boundary, so our temperature distribution is nice, it behaves in an orderly fashion, and conforms to how nature does things. Okay? So if we do that, we take number 1, this boundary. We know that the dt dx, the heat is flowing in the x direction. So this guy, at boundary, it's going to be at x equal w. Again, that's why I use 2w here. So we go up w. So x equals w. And all along y, we're going to have this condition. So we leave that as a variable. Okay? So that gets set equal to h over k, same guy. The surface temperature has to be along that surface, x equal w, and it's all along y. And you subtract that ambient temperature. Boom! Another boundary condition done. Next one is going to be at the tip of that fin. All right? So what we need is the heat transfer to flow through in the y direction, flow through this surface as such. So this guy becomes dt dy, because it's flowing in the y direction. The direction of the temperature differential drives that heat transfer. It's going to occur at y equals L along that boundary. And it's going to happen for all x, all along that area. Okay? So that is equal to, again, same balance, negative h over k, times the surface temperature. It's going to be at y equals L along x minus T infinity. Bam! That's the 4th boundary condition. Okay? So, we've got this guy here. We've got the equation of motion, which is sort of like the treasure map, which is dictating where to go, has all the information we need to derive the end result, get that value, find what we're looking for. And then we have these 4 boundary conditions due to heat transfer equivalency across the boundary, symmetry, and the constant temperature T0. These guys are the accessories through which we can take that map and go and get the work done, go and find what we're looking for, right? This is the physics that's incorporated with all the information that's instilled in that equation of motion. Okay? So we got all the ingredients we need. Next, what we're going to do is I'm going to start taking these boundary conditions and start using them to further simplify this guy. Okay? Because if you look at it right now, and as I made note of a little bit ago, right, we have 2 independent variables, x and y. It would be nice if we could eliminate them. And when you hear that, eliminate a variable, that might make you think of what we talked about with the BO number. We spent so much time deriving that non-dimensional parameter. And we're going to find that it's going to come in handy. We start messing around with some of these boundary conditions. We're going to find that the BO number pops out. And as a result of that, since we know that it's very small, that's going to allow us to eliminate some terms We're going to transform this. We're going to get an equation we can solve very easily, make our life easier, and get to that end result. Stay tuned.